Let's talk about how to find loop gain, especially in Spice. If you're watching this, I'm assuming that you've already know how to find loop gain by hand. Let's just review it. The first thing you have to do is find the operating point, and one of the main issues here is that you need the feedback to help you establish a decent operating point. But once you've found the operating point, you then convert that to a small signal equivalent circuit, which I'm showing here, and then you pull out pretty much any node that you want and break the feedback loop there, and you find the resistance seen looking into the input of the loop. By the way, this resistance, or in this case impedance, doesn't depend on feedback because the loop is broken, so you're just using the basic formulas. So you find that impedance, call it Z sub I, and then you make a copy of Z sub I and terminate the output side of the loop with that. And then you have two choices. You can either apply a test input voltage source to the input of the loop, call it Vx, and find the resulting Vy, and then the loop gain is Vy over Vx. I'm neglecting signs and things. Or you can break the loop somewhere, anywhere, and apply a current source to the input of the loop and find the resulting Iy that flows into the copy of the input impedance, and then the loop gain is the ratio of the output current Iy to Ix. It turns out if you're doing that in Spice, it's actually harder to do. The real issue is, when you're in Spice, if you have the loop closed, then it's easy for Spice to figure out what the DC value of this voltage is. And of course, the current in every branch is well established. But if you decide you need to break the loop, then you have a problem. Unless you've applied exactly the right DC value to the input of the loop, then there's no way that this value is going to be anywhere close, or it's unlikely that the value of this voltage will be even close enough for all the transistors inside the circuit to be in the right region of operation. That's especially a problem in high gain circuits like op amps. You really have to have the input specified to very high precision in order to get all the transistors even to work. There are some tricks you could do. You could make a copy of the circuit and close the loop. Let that copy of the circuit automatically figure out the value of DC of V of this voltage, and then apply that here, and then that would guarantee that this one has the right voltage, and the currents would take care of themselves, sort of, except for how are we going to find this input impedance? This is a small signal parameter. We don't have a real way of finding that automatically, so that really is not a successful way of doing it, and it's kind of a kludge anyway. So here's a clever way to do that. This is called Middlebrooks method, and it can work to get pretty much exactly the right loop gain. Here's the trick. We're going to make two copies of the circuit. In one copy of the circuit, we're going to apply a zero value DC voltage source, call it VZ. A zero value voltage source put in series with the feedback path means these two voltages are equal, but what they're equal to, the DC values of these voltages, is exactly the right voltage that we want, because this one's zero, these two are equal, these are equal to just what they should be, and the currents take care of themselves. And then in order to do AC small signal analysis, we give this VZ source, it's really an arbitrary value, but I would say just choose 1 volt AC, and then these two voltages are slightly different in AC. It doesn't matter how big the difference is. So whatever Vx is, that's applied to the input, and the output becomes Vy in AC analysis. And then you define a quantity T sub V, and I'm even doing the signs carefully here, and the actual loop gain of the circuit is approximately T sub V. If you've chosen where to break the loop so that the magnitude of the impedance Z sub I looking in here is much greater than the impedance Z sub O looking in there, again, these are without feedback, these two quantities. If this relationship holds to the extent that it holds, then the loop gain that you find by this formula and this analysis is is equal to the actual loop gain. It's not always easy to make sure this holds over all frequency. Maybe you can find a place in the circuit where the impedance looking into one part is much less than the impedance looking into the other part. If you do that, you can use this alternate version. Apply a zero value current source, zero value DC current source, IZ. With IZ equals 0 for DC means that the DC currents in these two branches are equal. And once again, they'll be equal to just the right currents, and this will be equal to the right voltage. but we give IZ an arbitrary AC value, to call it 1, and see what the ratio is of IY to IX. And again, accounting for signs, the ratio of IY to IX is T sub I, a current-based estimate of the loop gain. And to the extent that Z sub I magnitude is much less than ZO magnitude, then the actual loop gain will be approximately equal to this T sub I. Now, in general, it's not easy to know that either one of these conditions holds, especially over all frequencies. So by themselves, these aren't so good. So the idea of Middlebrooks method is you make 2 copies of the circuit. You use one of them to get the T sub V. You use the other one to get T sub I, and then you combine them by this complicated formula. All right. And the only other thing I'd say about it is that the formula you have to keep track of the signs. You even have to keep track of the phases, or you can use complex arithmetic. So it's a little complicated, 2 copies, a bunch of other stuff, but this will work. And in principle, this thing will compute the actual loop gain exactly. Now, there's a better way to do it, and I'm going to go through that in some detail, and I'll show you how it's done in SPICE. But the basic idea is that it's very similar to this, but we're going to be able to find these variables. And there's some tricks in the LT SPICE that you can use to make this work better. So to show you how that works, this is called Tien and Kundert's method. Kundert is at Cadence Corporation, and Tien, I don't know, was some grad student or something. And they wrote a paper about how to do this a while back. Let me see, where am I going here? Looking at myself in a mirror there. Okay, this is what I wanted to show you. So if you go to the LT SPICE files and you dig into the things, you can find a set of educational things, and they have a thing called loop gain. And this is what you see when you get in there. So what they've done here is they have sort of an arbitrary loop. There's just some op amp. That's not the point of this thing. And it's got a feedback loop here. The main point is they made 2 copies of the feedback loop. And in one of them, they added this little thing, which is a 0 value DC voltage source, AC value 1, you can see that. And then they found the ratio of the voltage at this node to this node in small signal analysis, and they call that G sub V. And then they did the same sort of thing over here. They have a 0 value DC current source I1, with an AC value of 1, and V3 and V4 are just used to find the currents through these things. And those currents through V3 and V4, the ratio of those currents with the signs taken care of gives you what they call G sub I, and then you have to plug this into this big formula. So that's the Middlebrook way of doing it, and that's pretty good. But then there's a better way, which is called the Tien method, and this is in the loop gain 2 file, and you see they only need 1 copy of the circuit, and then they play some tricks here, and I'm going to go through and show you all this stuff. But we're going to need to put this function in there. We'll have to have these node names, and the names have to be exactly right, and then we're going to do some tricks. I'll show you right here a little bit more detail about how that works. So again, we have an arbitrary feedback loop, and we have named this as node X, and we have a current source and a voltage source, and they have this rather complicated definition. It says the AC value of I sub I is the unit step function of a parameter called P sub R, and there's a similar one for the voltage source. P sub R is a thing that in the first simulation is -1, and in the second thing it's +1. Well, in the first simulation, when P sub R is -1, the unit step function of -1 is 0. This guy is off. The unit step function of -1 is positive and is equal to 1, so V sub I is equal to 1. So when P sub R is equal to -1, V sub I is 1, I sub I is 0, they find the current through V sub I and the voltage at V sub X. And that's all they're going to need. And then they, the simulation then sets it to 1, then that turns off the V sub I and turns on I sub I. And so they repeat the analysis. And then those can be combined in these formulas. So they needed some variables. So A is the current through V sub I in the second simulation. B is the current through V sub I in the first simulation. C is the value of the node voltage X in the second simulation. and so forth. All right. And then those are plugged into this formula that was derived in the paper by Tien et al., which you can go look up if you want to know all of this stuff. And they go through and they show if you plug into this formula, then you get the actual loop gain. And this is as a function of frequency. This is AC analysis. I noticed that, so you have to add this function into your SPICE file and this thing into your SPICE file. You actually have to be a little careful. People have screwed this up. This is the names of the sources have to match the names of the things in here. So this has to be V sub I, and this has to be called exactly I sub I. And then this node X has to be called node X. Well, one thing that people have screwed up before is they accidentally had another place in the circuit that was labeled with X, and of course the SPICE tied those two nodes together. At any rate, this is a little complicated. It seems complicated, but all you really have to do is just drop in this so-called loop breaker gizmo into your feedback loop. It doesn't even matter which is the input side and which is the output side. You can put it either way, and it still works. So it's very it's complicated, but you really don't have to know much about it. Once you've done this once, then you'll forget all the details of this and just say, oh, this is how I have to do it. And so now you know how to find loop gain using SPICE. Lucky you.